we're going to switch from studying gas laws to discussing kinetic molecular theory of gases. Remember that a law is a summary of a phenomenon. It's a statement of what happens every time. A theory is a proposed explanation for that phenomenon. A theory tries to explain why it happens that way. So kinetic molecular theory tries to explain why pressure and volume are inversely proportional, or why volume goes down when temperature goes down. This theory tries to explain why the laws exist. Kinetic theory of gases says that gases are composed of small, hard spheres spaced very far apart. Given the amount of space between the spheres versus the tiny size of the spheres themselves, kinetic theory says that the volume of the actual particles is insignificant. Also, kinetic theory says that there are no forces of attraction or repulsion between the particles. The particles are in constant, rapid, random, straight-line motion, and they only change directions if they hit something. Those collisions are considered to be perfectly elastic. That means that the gas particles don't lose any energy as a result of the collision. Lastly, kinetic theory says that the average kinetic energy of the particles in a sample is directly related to the Kelvin temperature. Let's talk about that last statement a little bit. Let's look at the connection between kinetic energy and temperature. As kinetic theory says, temperature is a measure of the average kinetic energy of all the particles in an object. Kinetic energy is the energy of motion, but kinetic energy is not the same thing as speed. Kinetic energy is related to both the mass and the velocity, which is something similar to speed, of the particles. Temperature is not a measure of the speed of the particles. Temperature is a measure of the kinetic energy. The speed of the particles is related actually to the square root of the temperature. Look at the kinetic energy equation again. Speed, actually velocity, is squared in the equation, so that speed is related to the square root of kinetic energy being temperature. Take a look at the graph. This shows the speed of oxygen molecules at different temperatures. At 273 Kelvin, the average molecule is traveling at around 250-ish meters per second. At 1000 Kelvin, the average particle is moving at around 650 meters per second. As the temperature increases, the average speed of the particles increases. But if you stopped and actually crunched the numbers, the relationship would be based on the square root of the temperature. This graph and this concept is usually referred to as Maxwell speed distributions, because James Clerk Maxwell first developed these ideas. And these speeds are called root mean square speeds. Root mean square speed can be calculated using the following equation, where R is the gas constant, T is temperature, and the mm on the bottom stands for molar mass. R is the gas constant, but this time we're going to use 8.31 joules over moles times Kelvin as the value. This is the value for the gas constant when the question involves energy of some form. Energy is measured in joules. A joule of energy is defined as a kilogram times meter squared per second squared. The only reason I mention this stuff is because you have to be careful to match units when performing root mean square speed calculations. Since joules are part of the gas constant units and joules are based on kilograms, your molar mass on the bottom has to be in kilograms. That's very unusual. We never see molar mass in kilograms except really here. But you have to put the molar mass in kilograms for the units to cancel properly. Here's an example problem. Calculate the root mean square speed of molecular chlorine in meters per second at 20 degrees Celsius. Calculate the root mean square speed. We're going to take the square root of 3 times R as 8.31 times the temperature in Kelvin divided by the molar mass in kilograms. Molecular chlorine, that's 2 chlorines, so it's 70.9 grams. In here we have to write 0.0709 kilograms. So the root mean square speed for chlorine molecules at roughly room temperature is 321 meters per second. So here we are again, describing a gas. By now, hopefully, you think of pressure as the force exerted on the walls of the container by the gas particles colliding with the inside walls. You think of temperature as a measure of the average kinetic energy of the particles in the sample. Volume is the amount of space the particles have to move around. And the number of particles, okay, that's still just the number of particles contained in the sample. Can you use kinetic theory to explain the relationships we see in the gas laws? If pressure is held constant, what happens to volume when temperature increases? Volume increases too. But why? Kinetic theory tells us that if temperature increases, that means the particles are moving faster. If the particles are moving faster, they'll collide with the container walls more often, pushing out the walls of a flexible container. Okay, at constant temperature, when volume decreases, the pressure increases. Why? If temperature is constant, the particles are moving at the same speed in both circumstances. The particles are going to hit the wall of the container the same number of times. If the volume of the container is lowered, that's the same number of hits over a smaller area. So, to say that another way, there's more hits per the amount of area available. More hits means greater pressure. When temperature increases in a rigid container, what happens to pressure? It increases. But can you explain why? A higher temperature means faster moving particles. Faster particles will hit the walls of the container more often. More hits means greater pressure. Also related to the speed of gas particles is Graham's law of effusion, which states that the rate of effusion of gases is inversely proportional to the square roots of their densities or molar masses when compared at identical pressures and temperatures. Effusion here is defined as the movement of gas particles through a tiny opening. Graham's law sounds really tricky, but to put it in simpler terms, the rate of effusion goes down as molar mass goes up. And that makes sense if you think about it. Which one's going to get out of a tiny hole faster? A tiny little particle or a big massive particle? Obviously, the tiny particles are going to be able to get out faster. Mathematically, Graham's law looks like this. Graham's law does not give you a specific speed. It tells you how much faster or slower one gas effuses than another. Notice in the equation that the substances are switched, they're flipped on the two sides. Rate A is on top, but its molar mass is on bottom on the other side. This Graham's law question asks us which effuses more rapidly, ammonia or hydrogen gas. So we need to substitute values into Graham's law. The question will be a little bit easier to answer if you put the larger molar mass on top. So that means write the rate of the smaller molecule over the rate of the larger molecule. So in this question, we'll put the rate of NH3 on top and the rate of HCl on bottom. And then we'll sub in the molar masses and solve. This answer comes out to approximately 1.5. That's the factor by which ammonia, what we put on top, effuses faster than HCl, what we put on bottom. So the answer to the question is ammonia effuses 1.5 times faster than HCl. Mathematically, Graham's law arises from setting up a ratio of root mean square speeds for two different gases. Remember, temperature is a measure of the kinetic energy of the particles. If the gases are at the same temperature, then the samples have the same kinetic energy. And remember that kinetic energy equals 1/2 mv squared. On this graph, we have three different gases with three different masses. O2 is the heaviest, H2 is the lightest. If their kinetic energy is the same, because their temperature is the same, and their mass decreases from O2 to CH4 to H2, then the velocity of the particles has to increase. Or, like we said before, as molar mass goes down, rate of diffusion goes up. Here's what I just said. Temperature is kinetic energy. Several samples at the same temperature means they have the same kinetic energy. Kinetic energy is defined as 1/2 mass times volume squared. If you have gases of different masses, but their kinetic energies are equal, it means their velocities must be different. And if mass is going down, that means the velocity is going up to keep kinetic energy at the same value. One more thing regarding the kinetic theory of gases. Kinetic theory describes an ideal gas. Sadly, there are no ideal gases. What we do have are real gases that behave ideally under some conditions. When considering real gases, kinetic theory has two shortcomings. First, gas particles do have some volume. This becomes especially significant when the pressure starts to creep up. At high pressures, the volume of the particles is no longer negligible. This results in a higher than predicted volume of the gas sample. Secondly, gas particles do feel forces of attraction between one another, especially as the temperature of the gas sample decreases. Try to imagine a bunch of tiny, lightweight magnets flying around in a container. At high temperatures, the little magnets are moving so fast that they can't really interact with each other. At lower temperatures, the little magnets would be moving slower. At some point, they'd be moving slow enough that they wouldn't just whiz past each other. As they approach, their magnetic forces would be able to take hold. The little magnets would attract each other and stick together. The same thing is true for gas particles. The lower the temperature, the stronger the attractions between the particles. As a result, the gas sample has a lower pressure than would be predicted by the ideal gas law. What this means is that real gases behave most ideally at low pressures and high temperatures. What constitutes a low pressure and a high temperature technically varies for each gas. For lots of gases, though, normal room pressures and temperatures are low pressures and high temperatures. As I said before, at high pressures, the volume of the particles results in a higher than predicted volume for the gas sample. At low temperatures, the effect of particle attractions is great enough to cause a lower than predicted pressure. So real gases don't really match up with ideal gas law calculations either. The error is often quite small, but it is a known error. For real gases, we have the van der Waals equation. This first bit of mess in brackets is a corrected pressure factor, and that second bit is a corrected volume factor. The A and the B that you see in there are constants for each gas. And you can look these up in your book or on the internet. Pressure has to be corrected because of the effect of the attractions between particles. And volume has to be corrected because we have to account for the fact that the particles themselves do have some volume. Most of the gas is still empty space, but some of the volume is taken up by the particles. And the more particles added, or the larger the particles, like xenon atoms are way bigger than helium atoms, the greater the deviation from ideal behavior.